6-7 is about finding the inverse of functions, and there's kind of 4 key things that we're going to look at with inverse functions. Today we're going to look at 2, and then in the next video we'll study kind of the last 2 properties of inverse functions. So I started with a picture of the inverse mohawk. If any of you football players cut your hair like this in the fall, I'd love to update my picture with someone that I actually know, so feel free to email that to me if you have one. What are inverse operations? Well, let's think of, if I say 10 and I add 2, to undo adding 2, I would subtract 2, and then I get back to where I started. So addition and subtraction would be inverse operations. Similarly, multiplication and division would be inverse operations. If I take a number times 2 and then I divide that by 2, I should be right back where I started. We also looked last chapter at if I square 10 and then take the square root, those would just undo each other and I'd be back at 10. Or same thing, if I cube 10 to get 1,000 and then take the cube root of 1,000, those would undo each other. So inverse functions or inverse relations, 4 key things. Here's the first property that we need to be aware of. The input and output values are interchanged. So in other words, the domain of the original relation or function becomes the range of the inverse relation or function, and the range of the original becomes the domain of the inverse. So one way to think of that is, I'm just going to switch the x and y values, which might make a little more sense once we actually look at an example here. Or what this is essentially saying is the domain and range switch. Okay, so what does this mean? Well, before we look at an example, the inverse of a function is denoted by this right here. So just so you know, this is read the inverse of f, or f inverse. It does not mean f to the negative 1 power. So if I see this, do not read it as f to the negative 1 power. I know we just studied exponents, but in this case, this is read the inverse of function f. And the inverse might not even be a function, so it might just be a relation. Remember, to be a function, each input would have to have one output. So now, if we actually look to our first example, let's say this up here is my original function. So I just have 7 points. You should have a note sheet. And by the way, let me go back here. So make sure that this is point number 1 on your note sheet. So if you need to pause the video, make a note, okay, the first property, the domain and range should be switched. Input and output values are interchanged. And then if you look at this graph from the note sheet that I gave you in class today, let's go ahead and plot these 7 points. So I'm going to pause the video and plot these points. You can do the same. Okay, so here are the 7 points of my function. Note that, this is not continuous. I have to pick up my pen to go from one point to the other. But what makes this a function is each input has exactly one output. This passes the vertical line test. There are no x values that repeat and map to different y's. If I want to find the inverse then, so what does this first property mean when I say the input and output values are interchanged? Well, if I want to find the inverse of a function, all I need to do are take these points and switch the x and y value. So my original function, by the way, this notation on the outside means it's a set of these 7 points. So the inverse would just be these 7 points, but I'm going to take the x and the y, and I'm just going to switch them. So the x becomes the y, or the domain becomes the range, and vice versa. Let's see, so -6, -6, 3, 5, and then there's our last point. And why don't you go ahead, pause the video, and graph these 7 points. Now there's a couple things to notice about the graph of the original function. and the inverse of the function. So here's one thing. These points do not move. So 2, 2, -6, -6, there's actually an overlap on the graph. Those points aren't moving anywhere. Another thing to make a note of is the inverse of the original function a function? So is this a function? And your answer should be no, not a function. Where are the problem points? Well, I mean, I can see right here, here, and here. I'm inputting 3, and one time I'm getting out 0. Here I'm inputting 3 and I'm getting out 4. Here I'm inputting 3 and I'm getting out 5. So if I input 3, I should always get out the same y value if this is a function. On the graph, you can see right there, those 3 points, the inverse relation fails the vertical line test. There's more than one point on the vertical line, x equals 3. So the original is a function, the inverse is not a function. Another thing to note, and a way to check that if your graph is correct, is there should be some symmetry here. What I mean is, if I take the original function and I draw a specific line and I reflect all the points over that line, I should get the inverse relation. So any ideas where the line of reflection might be? The line of reflection actually should be right here going down the middle. Let's make this green. So if you tilt your head a little bit here, if you can see, these points aren't moving because they're on the line of reflection. And then, if I kind of like trace through these points, there is some symmetry about that line. And the equation of the line is y equals x. So if I took all of the blue points and I reflected them over the line y equals x, I should get the points in the inverse relation. So for instance, this point right here, if I reflect it, would end there. This point, if I reflect over the line y equals x, would end there. This point's not moving because it's on the line y equals x. So that brings us to the second point. So make a note of this on your note sheet. The graph of the inverse of a relation is the reflection of the original relation over the line y equals x. So if I graph a function, I reflect it over the line y equals x, I would get what is called the inverse of the original function. So now the other key thing to this section is how do I actually find the inverse equation? So consider the function f of x equals 4x minus 1. I want to find the equation for the inverse. Well, remember, f of x is just like saying y. So this is my original function. If I want to find the inverse, keep in mind the domain and range should be switching, or the x and y values will be switching. So to find the inverse, all I need to do is switch the x and the y value. So this right now is actually the inverse equation, or I could call it f inverse. And now the only thing I want to do is I want to clean this up. So once I find the inverse, I actually want to write it in y equals form, so I could write it back in function notation form. So now all I need to do is solve for y. So I want to proceed, just get y by itself. Well, to get y by itself, first step I'd add 1. Then to get y by itself, divide everything by 4. So if I divide each side by 4, I'd be here. Or if you wanted to, you could actually split up this fraction. So if I wanted to write it as, 1/4 x plus 1/4, that would be perfectly legal. Remember, the 4 is attached to the x and the 1 since you're adding in the numerator. So if I split up the fraction, it would look something like this. And if I wanted to rewrite that using function notation, I could say, all right, the inverse of function f is actually 1/4 x, or x over 4, same thing, plus 1/4. Now, if I want to go ahead and graph this function, I mean, think to yourself, what should this look like? And what should this look like? Well, hopefully you've noticed these are both x to the first power. These would both be linear functions. So let's go ahead on the next page and graph the original function, which was f of x equals 4x minus 1. And the inverse function, which is 1/4 x plus 1/4. So recall how to graph lines. Start with your y-intercept. So if I plug in 0, I'd get out -1. My slope, rise 4, run 1, rise 4, run 1, or drop 4, back 1. Here's the original. And then the inverse function, the y-intercept is 1/4. If I plug in 0, I'd get out 1/4. Rise 1, run 4 is your slope. Rise 1, run 4. So the inverse would look something like that. So I thought I should get out lines. Yep, I do. And then just one additional check. Remember that the function and its inverse should be a reflection over the line y equals x. So if I actually, dot in that line y equals x, does it seem like if I reflected the blue line over the line y equals x that I would get the green line? Yeah, that seems very reasonable. And one additional note, if you solved this system and found the point that these had in common, they'd actually cross at 1/3, 1/3, which, yep, that's on the line y equals x, so that would be the point that's not moving if you reflected it. All right, so last example, using what we did on the previous example with the lines, maybe see how far you can get with finding the inverse of these functions. Okay, so first step, remember g of x is just like y, so think of this as y. And then you should have switched x and y, so if I want to find the inverse, switch x and y. And then I want to write this eventually using that function notation. So then I just have to go through and solve for y. Now all of this is together, so if I want to get rid of the fraction, you should have multiplied each side by 7. And then next step, you would have wanted to subtract 2, so 7x minus 2 would be y to the 5th power. And then how do you undo the 5th power? Well, I take the 5th root, or you could raise each side to the 1/5 power. So from here, either the 5th root or raise each side to the 1/5 power. And you'd end up at something that looks like this. And then let's go ahead and write this in the inverse function notation. So let's see, we started with function g. So I'm going to write this as the inverse of function g is the quantity 7x minus 2 to the 1/5 power. Or, maybe you wrote it as the 5th root of 7x minus 2. Both of those are perfectly correct. Now, I actually typed these into my graphing calculator. They're in the first 2 lines here. So if I hit graph, here's your 5th degree function. And here's what the inverse actually looks like. So that's that 5th root function. Notice how if I drew in the line y equals x, and I reflected the original, I should get the inverse function. So you can always use your graphing calculator to check that this is reasonable using that reflection piece, that it should be a reflection over the line y equals x. Back to the second one. Now be very, very careful. Make a note on this one. If I start by switching x and y, this is my inverse. Now I want to go ahead and put it in y equals form. So how do I undo the square? Well, I should take the square root. And now, wait a minute. If I have an even degree in the numerator, or if I have a fractional exponent and the numerator is even, so if I'm looking at the exponent, I have that even part, and I take the square root to undo the even exponent, I need to put that plus or minus sign out front. So the odd exponent, I'm fine. If my exponent's even, or if it was something like 2/3 or 4/5, I need to put the plus or minus out front. From here, I would proceed, so I would have plus or minus the square root of x equals, well, the square root and the square would cancel each other out. Then I'm going to subtract the 4. And last step, divide by 3. So my original was what, h of x, so the inverse of function h is plus or minus the square root of x minus 4 over 3. And certainly there'd be some domain restrictions here if I have the square root. If I look at the graph of this function, notice what happens if I don't have the plus or minus out front. So my original function, here it is on the bottom, that should be a parabola. So if I take the inverse but I don't have the plus or minus, let's see what happens if I graph these two. Here's the inverse. I only get kind of one branch of the parabola. So my original is this parabola. If I take the inverse and I don't put the plus or minus out front, I only get the one branch. If I put the plus or minus, then I'll get the other branch that I need to have the inverse of my original quadratic function. So the plus or minus becomes very important if the degree of the exponent is even.